Hi, everyone. My name is Kelly Dudley, and I'm with the News Center. And I'd like to welcome you to today's webinar entitled Getting to Know CTS Cement, How CSA Cement Enables Low Carbon Concrete. I'm so glad you could join us today. A video recording and PDF of the presentation you're about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Questions can be asked in the Q&A dialog box in the Zoom platform and will be answered once the presentation is finished. Attendees are in listen-only mode. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of the News Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixed components, among other things. You should consult your materials, cement, and concrete professionals for design assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. Okay, now I'd like to introduce our speaker today, Nick Ocampo. Nick is the Director of Sustainability and Senior Materials Engineer. He has worked for CTS for 17 years. He studied at UCLA, receiving a BS in Material Science and Engineering. He joined CTS Cement as a product development engineer and has held several positions working with a variety of product lines. When he is not answering questions about the environmental benefits of calcium sulfoaluminate cement, he manages bulk rapid set cement accounts in California and FastRock 500 customers nationwide. CTS Cement mission statement is, our mission is to provide the most innovative, highest quality construction products and solutions worldwide, with complete commitment to value, service, and customer connectivity. Okay, thanks, Nick. Go ahead and get started.
All right. Thank you, Kelly. Hello, everybody. For me, it's good morning, good afternoon to anyone else in the U.S. and a different time zone, and anywhere else joining us from abroad. But yeah, again, my name is Nick Ocampo. I'm the Director of Sustainability at CTS Cement. And yeah, let's just get right on with it. Quick presentation overview. I'll be discussing who CTS Cement is as a company, how we are involved with CSA Cement, discuss what calcium sulfoaluminate is, and the types of CSA cement that are available, how CSA cement achieves lower embodied carbons, where and when CSA is available, how CSA cements contribute to sustainability, and then if we've got time at the end before Q&A, get to some case studies and applications for some of our products. So with that, CTS Cement is the largest manufacturer of CSA cement. CTS Cement is the largest manufacturer of CSA cement in North America. CTS was founded in the 1960s following the discovery and development of CSA cement and CSA cement technologies. CSA was used in the 1980s, developing rapid set cement based on the CSA discovery. And we deliver CSA all across the country, as well as into Mexico and Canada, exporting to a variety of countries overseas as well. I want to note that CTS is an ESOP, an employee stock ownership program company. We are 100% employee owned. So every employee is an employee owner with a unique personal commitment to providing the best products and service to the industry. As an employee for 17 years, that's certainly true for me. And the main way I feel like I can deliver value is to discuss CTS's place in promoting the cement and concrete industry's sustainability goals. And that's why we're here with you today. So CSA cement was discovered by Dr. Alexander Klein at UC Berkeley. Dr. Klein was tasked with finding an expansive cement to combat the shrinkage that is evident in Portland cement. The compound, CSA cement compound, was named after Dr. Klein. It began being called as Klein's compound and is the foundation for expansive cement. That cement would further be developed as CSA cement, can hydrate into two different forms of etching crystals, depending on the chemical reaction with water. The first is the expansive material, and the second expands less but forms more rapidly, and that's the precursor to bolytic CSA, or what we call rapid set cement. I do want to discuss etchingite right now because etchingite in Portland cement is typically associated with destructive behavior. That's so-called delayed etchingite formation. And this is because etchingite forms after the cement has set. And because etchingite is expansive, it creates stresses within that cement matrix and creates cracking. CSA cement forms its etchingite very early. So these needle-like structures here on the slide form in the very beginning of hydration, prior to the development of any calcium silicate hydrate from B-lite or from other hydration products. So rather than being a destructive force, etchingite is actually a synergistic relationship to the other hydration products in the cement. So the needle-like crystals that form in the beginning serve as nucleation sites or as the backbone around which CSH and other products from hydration form. I'm not going to go through every point here on this timeline, but you'll see that the research began in 1958 with T.Y. Lin investing in expansive cement research, which Dr. Klein headed up. And that led to the discovery of CSA cement in 1964. He patented the Klein compound the following year. In 1975, the first production of type K cement, which is a blend of Klein's compound and Portland cement, was produced. That there's a first production run in 75. And the year after that, there was another patent issued to OST for a rapid hardening CSA cement technology, and that would become known as a rapid set. In 1987, CTS as a company acquired the patents and IP for both OST and Klein patents, and that really kickstarted the growth of CSA cement in the North American market and the development of CTS as a company. So I'm going to take a step back and talk about what is CSA cement. CSA, the abbreviation, is for calcium sulfoaluminate, calcium sulfoaluminate cement. In cement chemist notation, that's C4A3S bar. That S bar is for sulfur, so sulfur aluminate. The compounds in Portland are C2S and C3S. That S is for silicates. CSA is not a Portland cement. It does not fall under ASTM C150. It's not classified as one of the 5 types of Portland cement here in the US. It's not a GU or GU1, GU2 in Europe or elsewhere. It is, however, a hydraulic cement. It falls under ASTM C1600. It's a performance specification for rapid hardening hydraulic cement. There's also ASTM 1157, which is the general performance specification for hydraulic cements, but there is no rapid hardening category under that specification right now. There is effort to include that language into 1157. So if that language is approved, CSA cement and specifically rapid set cement would fall under 1157 as well as C1600. But with the way that cycles work in ASTM, that's probably not likely to happen if approved at all within the next year or so, just probably 5 years down the road or something like that. CSA cement does contain some compounds that are found in Portland cement, but at different proportions. I'll talk about that in the next slide. But more specifically, the mechanism for long-term strength gain is the same. It relies on B-lite, C2S, that provides long-term strength gain hydration beyond the first 2-3 days. CSA cements are made in the same kilns as Portland cement, either wet or dry. Both are possible. And like Portland cement, there are different categories or types of CSA cement. So there's a lot of the same and quite a bit that's different as well. I'm going to expand on that last point from a bit. This chart comes from ACI 242, ACI 242, the Committee for Alternative Cements, which defines 4 types of CSA cement. The first is type A. This is the CSA you'll primarily find manufactured in Europe or in Asia. This contains a high concentration of CSA cement, and it is intended to be blended with Portland cement in order to reduce set times and accelerate development of early strength. It does, of course, rely on the baseline Portland cement for its long-term strength gain. Type B, or Bolitic CSA, sometimes I've seen that flipped around as CSA B-lite in some literature and some research papers. Type B is BCSA. It is a standalone cement that has low shrinkage, rapid strength gains, and high ultimate strengths. Type C is the expansive component. That's very similar to what Klein's compound was discovered for and used in the 60s and continues to be used for that purpose to this day. This product is added to Portland cement to make type K shrinkage compensating cement or for chemical pre-stressing. And then type K is I call it a hybrid. It's a shrinkage compensating cement. It's a hybrid because type K is already defined under ASTM C845 for shrinkage compensating cements. But because CSA is a critical part of type K, it is listed by the 242 committee as a alternative cement under CSA. For reference, CTS Cement manufactures all four types of these CSA cements. FastRock 500 is our type A, which is supposed to be blended with Portland cement. Type B is our rapid set cement, which is by far the highest tonnage material we produce. And type C and type K cements are the cements that started this whole journey, component and type K. And for the rest of the presentation, I'm going to be primarily discussing type B CSA, rapid set cement, because of just the sheer volume at which we produce that. But I will be discussing type K and component as well for some specific applications and for the sustainability of that material. I do want to turn to the breakdown of the composition. I mentioned that these products are present in various quantities and proportions. Starting with alite, that second column, alite is responsible for early age strength gain in Portland cement. And that's why it's so high in type 3 cement, which is, our high early cement in Portland. If you look at the bottom for BCSA, there is no alite present. That CSA basically takes over all of that. If you remember, CSA is a C4 A3S, where alite is C3S. Basically, all of the calcium that is present in the kiln gets occupied by CSA. So there's not enough calcium to produce alite. The other reason is that alite is produced at a temperature range outside of the range of CSA and vice versa. So there's really no overlap depending on what the temperature of the kiln is for CSA to be produced versus alite. The second thing I do want to note is in the middle, B-lite, C2S. This is the product that is responsible for late age strength gain in both CSA cement and Portland cement. And you'll notice that in BCSA, there is a significant portion of B-lite. Actually, in this case, a little bit more B-lite than CSA. That's roughly around there. It's somewhere around that kind of 50-50 range. It could go up higher or lower depending on the manufacturer. But yeah, the B-lite is how strength gain contributes around the ettringite crystals that CSA forms early, creating a high early and durable product. This chart is from a 2018 study looking into the chemical CO2 emissions for each clinker compound, and you'll see at the top of the list that A-lite and B-lite are there, and they're both rather heavy contributors to chemical emissions at 579 kilograms per ton of A-lite produced, 512 kilograms of carbon for every metric ton of B-lite produced. And then if you go down, it was on the slide, I didn't mention it earlier, but the third from the bottom, yeelimite, that's the mineralogical name for CSA cement. That only emits 216 kilograms of carbon dioxide per ton of yeelimite produced. And the reason for that is it just simply requires less limestone in the kiln. So the chemical emissions are from the separation of calcium from the carbon and oxygen in limestone, whose chemical formula is CaCO3. And I'm sure I'm not going to be the first one to say this. I'm trying my best to avoid some of the things that everybody says, like the 8% for the industry, the contribution of emissions. Trying to avoid that, but one thing that I do need to say, and that I'm sure you've heard before, is that the carbon emissions from cement come from two primary locations. You probably heard from five primary locations, but in this case, I'll talk about the top two for CSA, which is calcination and combustion. In the previous slide, we talked about the chemical emissions. That is from the separation of the calcium from carbon and oxygen in limestone, CaCO3. So the calcium has to be freed up so it can bond with silicates in a Portland cement kiln and sulfates and aluminates in a CSA cement kiln to create CSA or to create the calcium silicates in Portland. And then the rest, the carbon and the oxygen, form CO2, and those are emitted. So because we use less limestone, or because CSA cements use less limestone in the raw mix, you get significantly less chemical emissions. The other thing is combustion. And as I mentioned with alite, the burn temperature of CSA is lower than alite. So where a Portland cement kiln is typically requires 1500, 1600 degrees Celsius for the reactions to occur, the reactions that form CSA happen at around 1280 degrees Celsius. So the burn temperature required is lower, which means less fuel needs to be burned, and that results in lower emissions. The background for all the CSA is necessary really to lay the groundwork for why we're here, why we're talking about all of this. and how it ties into embodied carbons and with new. Knowing what we know now, I like to say that CTS's sustainability journey started in the 60s and 70s with the discovery of CSA, and we've been making a low embodied carbon material since then. But more tangibly, the first time CTS documented carbon emissions was in 2008. In 2007, we hired a consultant to come to our plant and review the emissions at our plant. And at that time, he found that there were 610 kilograms of carbon dioxide per metric ton of rapid set produced. And then also compared that to the Portland cement produced at the plant, which was right around 900 kilograms per metric ton produced. So that's a reduction of roughly 33%. And that's kind of the number, the comparison that we ran with from 2008 all the way up to 2019. I do want to note that this analysis was a emissions at the plant only. So knowing what we know now about EPDs and life cycles, we did not include A1 and A2, the extraction and transportation of raw materials to the plant. So 610 is an emissions at the plant only. The 900 for the Portland is at the plant only. So that's why the numbers on here are a little bit different than the numbers here. So as we fast forward to 2019, driven primarily by the growing demand from the LEED rating system, USGBC's Green Building Code, and DOTs asking for more EPDs in the industry, we started our journey to produce an EPD and get GWP numbers for our bulk cements. So we published our first EPD in 2021 with putting the numbers, the GWP numbers, global warming potential numbers, at 728 kilograms of carbon dioxide equivalent per metric ton of our type A FastRock 500, 673 kilograms of CO2e per metric ton of rapid set. For type C, it's 461 kilograms of CO2e per metric ton. And then I also listed the industry standard or the industry average Portland cement and type 1L at 919 and 844 respectively, not for comparison, but for reference. I want to acknowledge that yes, but our EPD is plant specific, and the Portland and the type 1L are industry standard. So I'm aware of newer plants that have very clean processes, use renewable energy, use carbon capture and utilization, and the numbers out of that plant for a Portland cement are likely approaching the numbers of the CSA cements or possibly even lower. And I think, frankly, that's fantastic. The point of me discussing our EPD and discussing our GWP and having this webinar in general is not to say that CSA should replace all Portland cement. That's not anything that we're aspiring to do here. But the purposes of the webinar is to share the information and let folks know that this material exists and promote competition in the industry. I want to have more and more folks talking about, oh, I got our number lower. We got our number lower. The more that plans to push the GWP numbers lower, the better the industry is at trying to achieve the vision of 2050 of having a carbon neutral cement and having a carbon neutral industry. So I challenge everybody on here, anybody who's producing any cement, whether that's Portland cement, CSA cement, or some other alternative, or Portland in a non-traditional kiln. Get those numbers out there, and let's work together to get this number down. So all this talk about sustainable virtues of CSA are great, but if we can't bring a product to market, then there's really not a point in talking about it. So this is really the answer to the when and where CSA cement is available. And if it hasn't been apparent yet, the when is right now, and when is frankly for the past several decades. And where for CTS is pretty much all over the continent. We have a variety of distribution channels to bring CSA cement technology to the end user and to insert into service in society. We work with home center chains like Home Depot, supply yards like Whitecap, and we deliver bulk cement to concrete producers throughout the country. And those concrete producers then deliver to DOTs, airports, commercial and industrial projects, and even coal mines and hard rock mines. We also have custom mix designs that are approved and designed for the US military. So CSA cement continues to be an at-scale solution available all over the continent and in many countries throughout the world. So we'll talk about the bulk rapid set cement. One of the primary ways we deliver is via bulk. We've been delivering bulk cement to market for over 50 years, starting with type K. And the primary way we move cement around the continent and around the country is via rail. We can also deliver that via bulk trucks or bulk trucks from the rail siding to the end user, or bag into bulk bags for smaller jobs or applications where people can't handle bulk. Rapid set can be delivered in ready mix and volumetric trucks. I do want to be realistic here. I'm not saying that, it's July 31st that you should go out into the middle of Texas and try to put rapid set concrete into a ready mix truck. That's an uphill battle. We're not trying to accelerate an already accelerating process, right? But given the right circumstances and experienced crews, it can be done. And we have a perfect example of this up in the Pacific Northwest. We have a regional manager who's done great work over the years, uh, building a relationship with ready-mix operators. And in the Pacific Northwest, they're able to extend the construction season in the milder climate. And as it turns to winter, using rapid set concrete, they can take advantage of the cooler climates, and using proper retarders and hydration stabilizers have had great success in Washington State and Oregon, placing rapid set concrete out of a ready-mix truck. For most other applications and regions, volumetric trucks are fantastic and deliver rapid set cement and fantastically. And I don't want to say that we're limited to the Pacific Northwest, but I do want to highlight the fact that we have great case studies out there for ready mix operations. The primary applications for bulk works are pavements, specifically highways and bridges. We're not limited to that, but certainly that's kind of our bread and butter. We're based in California, CTS Cement is, but we have regional managers and crews all over the country. But here in California, we've done lots of work on Caltrans roads. Over 450,000 cubic yards of rapid set concrete have been placed since 1995. And again, in California, speed is especially critical for high traffic areas like San Francisco, Los Angeles, and Sacramento. It's also important to make sure that we limit closures on important freight lanes like I-5, 101, where we've had trucks that are delivering goods, food, etc., all over California and then throughout the country. So we want to minimize the closures as best we can. We can have closures as short as 5 hours for a panel repair, where a crew will come in, cut out a slab, concrete truck will come in and place the concrete, achieve 400 psi flexural strength in 4 hours, which is what's required to open traffic here in California. Or it could be 300 psi, 3,000 psi, or 4,000 psi compressive, depending on the specification in other states' DOTs. This is a similar case for airports, where rapid repairs are critical to get runways back in service and minimize delays. In some cases, a repair on a runway intersection could potentially shut the whole airport down if not taken care of in a timely manner. So thanks to overnight repairs, crews are able to come in, replace the panel, and have that section open for the first touchdown of aircraft at dawn the next morning. And a third application would be military. The Army Corps of Engineers has approved several custom bagged and box mix designs, bulk and bag mix designs, repairing critical military infrastructure. And this is especially important for repairing cracks and craters on military airfields. In the case of damage or explosive attacks, if there's airfields near enemy lines, these mixes are designed that any GI unit can come in, place the CSA cement repair material, and have a damaged runway back and up and running to allow aircrafts to take off to provide support, and perhaps more importantly, to get planes that may already be in the air landed and back safe on the ground. So with a bulk rapid set, it's difficult to give a blanket overview, as every mix design and application is unique. And then I'm talking about rapid set, the type B CSA. And we know that CSA can be blended with Portland for the type A and the type C, and that's going to depend on the baseline performance of Portland cement. And CSA can be used not just in concretes, but as grouts, mortars, and self-levelers, which I'll talk about a little bit later. It can be used even as shotcretes or 3D printing applications. But with all that said, a typical rapid set concrete mix design is going to have roughly 6,500 psi compressive strength as a design strength. Doesn't mean it can't exceed that, but that's what it's designed for. The initial set can be as fast as 15 minutes, but can be extended, as in the case of like the Pacific Northwest, to have an hour of mixing time. The product is expected to be low shrinkage, right around 0.02% at a reasonable water cement ratio. And in most applications, it can be used in most applications where Portland cement is used, so long as crews are ready for the accelerated working times. So I'm going to switch gears now away from bulk and over to our packaged products. We have over 50 cementitious packaged products. At least that's how many we have on our website. And I'm highlighting 6 to demonstrate a variety of use cases and applications. The first 3 on the left, mortar mix, or cementol, mortar mix, and concrete mix, are our bread and butter. They're pretty much keep it simple formulations, designed to be as all-purpose as possible. All of these are going to achieve 2,500 to 3,000 psi in 1 hour, as mixed for the instructions on the bag. And then the 3 products on the right are all formulated with admixtures for specific applications. So we get more into tailor-made products. With concrete resurfacer, used to restore old and spalled concrete, starting from 2 inches thick all the way up to 2 feet thick. VO repair mix is for vertical and overhead applications, as the abbreviation implies. And that has self-curing admixtures and retarders to extend working time. And then DOT repair mix is formulated to cater to higher performance specifications for DOTs, certain specifications that might be more demanding than folks that pick this stuff up out of the Home Depot might require. I should note that each of these products has a lead evaluation that's created internally that demonstrate the ways that these products can contribute to the lead rating system and can comply with various credits. If there's a structure or a building that's going after lead certification. And we are in the process of developing EPDs for the bag products. The caveat there is that we know we can't compare a bagged product to a bulk concrete. That doesn't make sense. If A1 to A3 for a bag product is getting the product in the bag and into getting that out to sale, versus a ready mix truck or a volumetric production where the end of A3 is adding water and having that ready to place. That there's no way to properly compare that. So a PCR is required. A new PCR is required for bagged products so that we can properly compare one bagged product to another. We picked out another set of packaged products here. This is what we call our flooring line. It's a line of self-leveling products. And this started out as a single self-leveling underlayment product, but as contractors quickly picked up on the fact that CSA allows for rapid hardening materials, or rapid hardening overlays, and has low shrinkage, they found it great for polishing and making polished concrete overlays. And that one product turned into an entire line of products. And in a similar fashion to the previous slide, I can say that I've participated in the PCR committee for polished concrete systems. And while a lot of that has to do with the actual system of grinding and polishing existing concrete, there is language for using a topping and bringing that, polishing that topping. Obviously, if you have to put in additional material, that's going to add financial and DWP costs to the project. So it's preferable to use existing concrete, but in cases where there's an engineering reason, an architectural reason, or simply a design and aesthetic reason why a topping should be placed, there's a solution for that. And we have, because it's powered by Rapid Set Cement, it's a lower embodied carbon material. I'm going to switch back to bulk and back to really the beginning in terms of component and the shrinkage compensating material. Component is the extension of what Climax Compound was discovered to do. It's typically blended with Portland cement. It expands for the first 7 days, wet cured, as is demonstrated on the chart on the right there, that blue kind of thick curve there, where it's meant to expand for the first 7 days, and then the wet cure is removed. It starts to dry cure, and based on the expected shrinkage of the Portland cement, is supposed to come down to basically dimensionally stable as 0 expansion, 0 shrinkage material. A typical replacement for component into Portland cement is around 15%, but if the Portland cement has low shrinkage, that can be as low as 10 to 15%. And if it is high shrinkage material for whatever reason, we can dose that higher for additional expansion to compensate for the added shrinkage that's expected. Type K is a pre-blended version of this, and System K is Type K with microfibers added for additional restraint. Component is great for applications where reducing control joints is critical. Things like large warehouses, distribution centers, water containment structures are examples of where this would be key. With the goal of a near dimensionally stable product, component allows for larger spaces between joints, minimizing slab curling, which minimizes the amount of wear on machines, forklifts, heavy equipment that would be going over this. And then, of course, minimizing the amount of damage that happens to the floor itself as these products go over. So there's costs associated with reducing the amount of wear and tear on equipment that goes over these and the floor itself. So there's savings both cost-wise and emissions-wise with the maintenance and repairs of that material. So I know I've talked a lot about the performance, done a little bit of sales there. I apologize for that. But the reason I went over all these performance characteristics and all these different varieties of applications of CSA cement is really to demonstrate that performance is tied in with sustainability and resilience. Generally speaking, most folks who turn and have used CSA basically for most of the life of CSA's existence have not really turned to it with sustainability or the environment in mind. They're turning to it for the speed, for the various performance advantages that CSA provides. But that doesn't mean that CSA cement isn't and hasn't always been intrinsically lower in embodied carbons this whole time. We saw in that table, yeelimite is simply just a low chemical emissions material. And it doesn't mean that the desired performance traits don't also play a part in sustainability, whether or not that was the intention of that product being used. So, for example, the speed of CSA enables contractors to open lanes and roads faster than otherwise capable. That's done to alleviate pressure and costs for the public, but that also means that there's less emissions associated with closures, associated with idling of traffic that might be happening during the daytime, or diversion of traffic for much longer routes to their destinations. The longer life cycle is directly tied to the durability or the resilience of the material, and that helps reduce the consumption of raw materials and emissions associated with manufacturing more cement and more concrete. Low shrinkage helps extend life cycles. It reduces cracks, reduces the amount of maintenance and repairs and replacements that might be associated with cracking in a concrete member. And the lighter color is something that we don't often talk about. CSA cement is often lighter in color, which for outdoor applications reduces the heat island effect, particularly in urban environments where larger quantities of hardscapes and structures using, if they're asphalts or if there's dark colors, will absorb more of the sun's light. And as it absorbs more light, it emits heat in that area. So having lighter colored hardscapes or roofs and structures reflects more of the sun's light, reduces the heat island effect, and effectively alleviates some of the pressure of other systems like cooling and air conditioning that would have to be increased because of the increase of however many degrees for the heat island effect. So I'm going to investigate more closely how speed contributes to sustainability. I mentioned it a little bit earlier. The speed of rapid set is demonstrated in this chart. If you look at the left side, that red curve reaches 3,000 psi within about 1 or 2 hours. And again, this is the result of CSA hydrating into etching crystals, developing that early strength very early. But I do want to point out that after the first 72 hours, it has the same steady strength gain over time that more or less parallels that of Portland cement. And that is because of the presence of B-light that is the mechanism for strength gain for both products. And so there basically is no strength regression or strength drop off over time with rapid set cement, with CSA B-light cement. So we know it's fast, but why is it relevant to sustainability? It's often said sustainability is not just about the environment. It refers to financial, it refers to community and social aspects, and of course, it refers to environmental aspects. So let's take the case of pavements, specifically roads and airports. If you have to close down runways, lanes, or the entire road, it's the repair and replacement is costly not just to the owning entity, but to the commuting public that has to use those pavements and has to drive around those pavements. That's the social aspect. On the slide, this is data from 2019, but it goes over the financial costs of traffic congestion. For the cost of drivers for traffic congestion is over $1,300 annually, costing 99 hours of driving time in traffic for a total of $88 billion of to drivers as a result of traffic congestion. And if you look specifically at the freight sector, $74 billion in costs, with 66.1 billion coming from urban areas and congestion in those areas. The situation is similar for airlines, with delays accounting for $33 billion of costs, and the majority of which is fronted by airlines and passengers themselves. And this is where CSA cement and rapid set cement can come into play. With concrete that can reach 3,000 psi in under 4 hours, the length of closures can be reduced, and that can alleviate large portions of this congestion, which typically occur during traffic, rush hour, daytime hours. So if you can transition a closure from a weekend closure to a 24-hour closure, or a 24-hour closure to an overnight closure, you can drastically reduce the impact of traffic congestion to the commuting public, which will then reduce the financial costs and the emissions associated with idling and diverting traffic. And it just so happens that the Iowa State University CP Tech Center late in 2024 put out a study. This is a study by Dr. Chang-Mo Kim that compares the emissions resulting from construction work zones in 3 different cases for a 24-hour closure versus a 10-hour overnight closure. I should note that this study mentions that for a 10-hour closure, it assumes that a rapid hardening concrete would have to be used to accomplish that. But if I could steal a phrase from the low carbon concrete code folks, ACI 232, essentially the study is technology agnostic. It doesn't say anything about CSA or Portland cement. It just says use a rapid hardening cement. That's the assumption. So CSA is not mentioned at all, but I do think it's important to discuss this study because when they review the 3 cases, the I-95 in Florida as the urban environment, the I-80 in Wyoming as a suburban case, and US 71 in Iowa for the rural case, the results are clear, and it might be a little bit hard to see. I'll throw up the laser pointer right here at this 48 million. If you recall in the previous slide, 93% of the freight costs associated with congestion came from urban areas. That's basically true here, and possibly even more drastically in this study. The study reported a difference of 48 million kilograms of carbon dioxide emissions per lane mile of construction when using a 24-hour closure in the urban environment versus a 10-hour closure. So it is just simply a massive amount of CO2 emissions saved if you can avoid all of that traffic congestion in the urban environment by utilizing an overnight closure, a 10-hour closure. I should note that the suburban and rural locales also showed an emission savings, roughly 2,000, 3,000, 2,600 kilograms of CO2 per lane mile. But I mean, that's nothing in compared to the 48 million that they look at. Now, I'm not saying that this is going to be the case for every, I'm not saying, and the study isn't saying that that's going to be the case for every urban environment. But hopefully the point stands and we kind of understand that there can be a massive, 1, financial impact, 2, social impact of all these drivers that are frustrated being in traffic, and 3, the environmental impact of the emissions that are avoided by utilizing an overnight closure. I do want to stress for the placing and finishing of rapid set concrete, especially if you're in an overnight closure, the placing and finishing of rapid set cement is nearly identical to that of Portland cement. You use the same consolidation methods, screeds, floats, anything you would on a traditional Portland cement job site. However, there is one very important caveat. It's speed. The thing to note is that crews absolutely have to be trained and organized. We're still talking about speed to account for how fast this material is going to gain strength. It's imperative to remind them that even the most experienced crews, if they're not familiar with a CSA cement job, placing and finishing curing have to happen within accelerated time frame. Even a mix that has been dosed with retarders or hydration stabilizers, while that'll give you additional time, once it starts to kick, it's really going to go off. So please make sure that the desired finish gets on early and the crews are ready to clean out any equipment, augers, chutes, things that need to be cleaned so that you don't have damage to any equipment or machinery. I'm going to switch gears to shrinkage now. Again, CSA cement was developed in the 60s and 70s to combat shrinkage in Portland cement. So as we discussed earlier, shrinkage is going to lead to cracking and curling, which causes wear to vehicles. These are all things that we want to minimize for social, financial, and environmental aspects. This chart here shows a comparison between 2 rapid hardening concretes, so we're still talking about speed. Following ASTM 1157. This is a quantitative way to measure the amount of length change going on in a concrete specimen. So the rapid set concrete exhibits the red line up at the top exhibits less than 0.02% shrinkage at 28 days. And I believe it's ACI, one of ACI's says that the threshold for cracking is at 0.025. So if you're under 0.025, it's expected that material is not going to crack, or at least not at that time frame. However, the accelerated Portland cement shows shrinkage in excess of 0.1% at 28 days. So that's 5 times the amount of shrinkage as the rapid set mix. So we definitely expect the accelerated Portland cement to crack. And we can see that in another test. This is another type of shrinkage test we call the ring test. It's ASTM C1581. Rather than having an unrestrained bar, like in ASTM C1157, which is great for quantifying the amount of shrinkage, here we're testing basically how long it's going to take for a material to crack, because we know that all concretes will shrink. So if we cast the concrete into the ring, it ends up looking like a big concrete donut, and with the steel ring on the inside is a mold and is a restraint, and there's a strain gauge attached to that internal ring. And as the concrete shrinks, it presses on the steel ring, and that steel ring will contract with elastic contraction, measure the microstrains, and eventually, as the pressure builds on that ring and the ring pushes back on the concrete, greater amounts of shrinkage lead to greater amounts of pressure, and that will cause the ring to crack. So on the chart here on the left, we can follow the accelerated Portland cement, the gray line, all the way down to 3 days, where you have 50 microstrains of shrinkage. It continues to shrink between 3 and 4 days to about 60, 65 microstrains, at which point the stress is too much and it cracks. If you look at the rapid set ring, we only get less than 10 microstrains for the rapid set material, and because it never builds up enough pressure, it doesn't crack. Even it gets to less than 10 microstrains at 7 days, and we have had multiple specimens in these ring tests for over 365 days, and so long as the shrinkage remains less than 10 or 20 microstrains, that material does not crack. So the question is, how is the shrinkage lower? And the answer to that lies in the amount of water that's required to hydrate CSA cement. I've often heard it said that the water demand in CSA cement is higher, and while that's technically true, that doesn't necessarily mean that the water cement ratio is anything crazy or out of the ordinary for the concrete mix design. The real reason in our minds that why the difference is so stark is that in Portland cement concrete, most of the water, or a significant portion of the water, is basically water of convenience. 0.25 water cement ratio is really required to hydrate the Portland cement, and the remainder is there for workability. And if it's not bound, then it's available to evaporate and eventually cause some shrinkage. In a CSA cement, at a 0.45 water cement ratio, 99% of that water is going to be used to fully hydrate the material, hydrate CSA and hydrate B-late. And if you'll indulge me for one slide as I nerd out over chemistry here, I want to talk about why CSA cement has such a water demand. The hydration reaction of CSA cement is listed right here. It requires 96 moles of water for 1 mole of CSA. And when we talk about chemical formulas, a mole doesn't necessarily mean like equate to volume or equate to mass, right? A compound of CSA is very big, so practically speaking, it's not quite as drastic, but it is interesting to just look at. The comparison is striking. For the 2 chemical equations for Portland cement, it's 3.5 moles needed for A-lite, 2.5 moles needed for B-lite. So it's 32 times more moles of water to hydrate a single CSA compound versus A-lite or B-lite, assuming roughly equal proportions. And again, this doesn't mean that it requires 32 times much of volume of water. That would be ridiculous. That's obviously not the case. But as seen in the previous slide, a 0.45 water cement ratio is needed to hydrate all of the CSA and a good portion of the B-lite, where a 0.25 is required for the Portland cement. So it's roughly twice the amount of water, but practically speaking, the water cement ratios are going to be pretty much standard at around 0.3 to 0.5, depending on what kind of slumps or what kind of workability you're looking for. And of course, what water reducers are being used. You can use water reducers in Portland cement to minimize the amount of water, amount of free water, water of convenience that's available in there to minimize that shrinkage. Same could be done for CSA cement as well. One last thing related to chemistry before I get off chemistry is sulfate attack in Portland cement. I talked about this way back, looks like 45 minutes ago now, that because delayed etching and formation is the mechanism for sulfate attack in Portland cement, even with a type 2, which is starting to have a little bit less C3A and higher sulfate resistance, after 2 years in a sulfate environment, that cube on the left sees some significant deterioration as delayed etching and formation occurs. In the CSA cement, because there is no C3A present, it simply has nothing for sulfate to attack. And there's, after 6 years of being exposed to a sulfate environment, the CSA cement block shows very little, if no, deterioration as a result of delayed etching formation. So I'm going to go over quickly. I don't have too much time, and I want to keep some time open for question and answers at the end. But some case studies and project profiles. As I mentioned previously, we have a great relationship with the Whitecap. We've been working with them for 21 years as a distributor, getting our 30 products out and around the US and Canada. We're very proud of our relationship with the Home Depot. We've been working with them for 15 years and have been awarded Vendor of the Year every odd year since 2013. So we're proud of our relationship with them. It seems like they're proud of their relationship with us. We have over 30 products and SKUs available in stores. So this is something you can just go down to your local Home Depot, head into the concrete aisle, and find the Rapid Set Bay and go ahead and pick up a product if you're interested in CSA cement materials. We are in, I believe, every store of Home Depot in the US. I want to say every store in Mexico, and we're in a good portion of the stores in Canada. I think there's a little bit of a regionality with where we're available in Canada. But yeah, it's been a great relationship. And again, in terms of where it's available, just drive down to your local Home Depot. You'll find Rapids out there. And a few case studies. This is the Cementol that I mentioned in a previous slide. Cementol was used here to restore some architectural members on these columns and arches at Caltech University down in Southern California. This is a technology I didn't talk about in this. This is the Thornburg Bridge and PA. This is Rapid Set Latex Modified Concrete, RSLMC. Latex is added to the bulk concrete production to prevent the intrusion of chlorides, specifically chlorides from de-icing salts from penetrating into the concrete and getting into the rebar below. If those chlorides can come through and reach the rebar, it's going to cause rusting and corrosion, which will reduce the service life and possibly damage the bridge. So the addition of latex to the mix serves as a corrosion inhibitor. We have another option for corrosion inhibition. That's low P. That's an admixture that CTS has available. It's called our low P admixture. It's available as both a powder and as a liquid. So this is an example of a low P concrete in Oregon over the Columbia River. It's another bridge deck, and it's an alternative to latex. So it's the same concept. Low P is added and inhibits penetration of water carrying chlorides into the concrete and keeps any chlorides from brackish water or de-icing salts from diffusing into the concrete and preventing it from attacking the steel and reinforcement. And again, this is just another way to extend the service life and keep this material in service for as long as possible. This is a true self-leveling in a museum setting. Looks to me that this has not been polished, like I was mentioning earlier. Polished would have more of the aggregate exposed. So this is kind of like a nice matte finish with a cement texture on top. But yeah, really, this just demonstrates kind of one way of having a really beautiful minimalist floor that lets the glass exhibits take the spotlight. Getting away from kind of the more beautiful things. This is some precast pipe repair. Also beautiful, not not different kind of beauty. But this is rapid set mortar mix plus being used, basically just troweling on. If you notice this piece of pipe that was damaged here, they're basically repairing that. So rather than having to toss or replace that pipe, we can come in with mortar mix plus, trowel that on, get the necessary finish that will harden, achieve 3000 psi in a few hours, ensuring a very fast repair and the smooth surface that's required, and that it's meant to have in order for these pipes to fit and function properly when placed. This is just a standard rapid set concrete repair job on the Monitor Merrimack Tunnel in Virginia, or connecting Virginia and New Jersey, if I'm not mistaken. Definitely an application where you want to minimize the length of the closure. You cannot have that tunnel down for an extended period of time. So this was a single panel, likely cut out and replaced in I would have to guess this was probably a 2-3 hour time frame by the time they got that out. And the crew on hand is there, quickly putting the finish on. Doesn't look like it started to set. That still looks like it's nice and moist. So they're definitely putting on the water cure and keeping things moving, and that should be set within an hour or two, or at least an hour or two from the time this uh, photo was taken. Put this up. This is a 3D printed reef wall using rapid set concrete. Just kind of a neat application demonstrating the type of structures and artistic forms or functional forms that can be done without using, or that would be very difficult to do without a form, and certainly not able to be done unless there's somebody on a boat doing that by hand. This is rapid set WonderFix being used to patch bug holes and any imperfections on tilt-up construction. This is a distribution center. WonderFix is a sandless material that can be used to patch up any bug holes or imperfections on a wall. And the beauty of this product is that it is sandable. So once you go through, put on your child finish, if there's any areas of imperfection, any other imperfections from putting on the WonderFix, or any areas that need to be brought down to surface to plane, you just come through with sandpaper and get that down to the finish that you're looking for. I-70 bridge in Colorado. This is rapid set mortar mix. Not too much to state here, but they just came in and put on the mortar mix where this pillar was damaged to make sure that the loads are being properly distributed and transferred down to the footing. I want to talk a little bit about this project. This is a project near and dear to my heart. I wasn't on this project, but this is the I-280 in San Francisco. They repaired some seismic hinges. This is a structural repair of 4 bridge hinges, 60-foot wide, 20-foot long, and 5-foot thick. And they achieved this using rapid set self-consolidating mix design. The producer put together their self-consolidating admixtures, all sorts of plasticizers and things, and hydration stabilizers to get 1 hour of workability and still have 0.019% shrinkage. It achieved 4,000 psi in 4 hours. And in terms of the self-consolidating, this was a 30-inch displacement for the self-consolidating metrics. I do want to note also that this was, if I'm not mistaken, this was about 10 years ago that this was done. They were supposed to do this, Caltrans was supposed to do this over, I want to say 3, 4, 5 holiday weekend closures because of how large the replacements were necessary. And we got this done, I want to say 2.5 closures. So because of the speed and the efficiency of the crews and the technology itself, we were able to drastically reduce the number of closures and get this open to the public, because the 280 is a very important artery in terms of getting folks in and out of San Francisco. I'm going to go through these a little bit quickly. This is true PC that is polished, true polished concrete. This is a retail space. I'd have to guess it's either Target or CVS based on the color here. And then the only other hint I have is that it must be in New York because we've got the Cat's Deli thing right there, signage. One more application for rapid set cement all. The first one I showed was those architectural pieces. This is another application where cement all was used, put into fabric forms, and use robotic arms to mix and consolidate these into a variety of very unique, almost countless ways, geometric forms that these robots could get the cement all members together. and that was used to create this custom artistic work. And then my last slide, as I really come up on time, is a distribution center where component was being used to overcome negative volume change. Again, this is another example of a floor where they extended construction joints with 150-foot spacing, and they didn't have to saw cut any of those. So that minimized the amount of dust and the amount of exposure to the workers on site. So that component floor being close to dimensionally stable was able to have those extended control joints, or extended construction joints, and will have minimal repairs going forward. So it looks like we have about 3 minutes left before the top of the hour. I do want to thank everybody for your attention. I hope you learned something about CSA. If you have any questions for me, if we can't get to them now, Kelly, I think we'll be taking questions, and if we can't get to them now, we'll get to them offline later.
We do just have a few questions. First of all, thank you so much, Nick. That was a really great presentation. I appreciate your time.
Thank you.
We do have a few moments. If anyone wants to answer any, ask any questions in the Q&A box, feel free to do so right now. We just have a few questions to get to. So as I'm going through these, feel free to add a few more if you'd like. Okay, let's see what we have here. Which product do you recommend for ICF bearing wall and ceilings?
Yeah, I'm sorry. That's probably one that I'm going to have to defer to my technical team
Okay.
for ICF. Yeah, we have a lot of products, so I wish I could answer that now, but that's definitely something I will send that over to me, and we'll get that answer to them.
Sure, not a problem. Okay, another one we have is, how do you approach or solve for possible products or businesses where you have to train the stakeholders to use CSA cement?
Yeah, that is. I'm not gonna say it's a challenge. I like to look at it as an opportunity. But yeah, we have a program where we have trainings. That's one of my jobs here in California, and we have regional sales managers across the country whose job is to interface with contractors, with DOTs, and have a program. I believe we call it a just-in-time training program, where we really go in and either set up a lunch and learn, or have some sort of training session where we help the folks, either whether it's volumetric or ready mix, come in, calibrate in the case of a volumetric, do some custom or trial batches for a central mix plant, and just really get people to understand what it feels like to be working with CSA cement, to be working with a rapid set material, and to kind of get over some of the hurdles that you might not experience or think about if you have an extensive background in Portland cement. There's things you might be taking for granted in terms of the speed and all that. But we do have a whole staff that is ready to have meetings and train folks up to use that. And for the most part, folks are pretty receptive to it. Certainly that there can be times where it doesn't always work out, but education and training is our, that's what we rely on, and just constant communication to keep things moving and succeed on a project. Yeah.
Okay, thank you. Okay, a couple more and then we'll be finished. Are there any issues with hydration heat? And do you use any special curing equipment at a job site?
Heat of hydration, that's a question that comes up a lot. I wouldn't say that it's a common question. I don't know that it is a critical concern necessarily. Heat of hydration, it depends on the application. But yeah, I could probably refer that to someone on the technical team to answer more thoroughly.
Okay.
But we are aware that the heat of hydration is slightly higher. But typically speaking, if we're talking about a pavement, there's not too much. There's enough mitigating factor in terms of the substrate and the environment, where heat of hydration doesn't cause any sort of thermal cracking or anything like that. There would be applications where that might be an issue, but I'd say on most applications that's not much of a problem. And what was the second half of that question?
Let's see. Do you use any special curing equipment?
Um, Not necessarily curing. We recommend for the most part water curing. Burlap, wet burlap is our preferred method, I would say. Curing compounds work as well. We say that the type 2 PAMPs curing, if I'm not mistaken. and we want to just make sure that if you're following DOT specifications for putting curing compounds down on the pavements or slabs. I am talking about pavements right now, but yeah, if you're curing structures, vertical structures, foggers, misters, anything you can do to keep the hydration going. But anything that you would use for Portland cement in terms of curing, you could more than likely use for a CSA cement.
Okay, and then we look like I have one more question and we can wrap up. Which product do you recommend for shotcrete?
We have a few tailored shotcrete products. Um, I'm going to stop there before I get myself into trouble and
Okay.
recommend a current bag product. That's something I'd like to discuss with that individual offline in terms of what we'd recommend for shotcrete.
Okay, well, thank you again, Nick. We appreciate your time. I want to remind everyone to please visit the new website at newconcrete.org for more information. While you're there, please check out our resources on lower carbon concrete production and placement. Our website provides access to our sustainable concrete guides, frequently asked questions, webinar recordings, and more. And please stay tuned for our next webinar taking place on August 28th, presented by Ash Grove Cement. Thank you again for attending today's webinar, and please stay tuned for future webinars. Thank you. Have a great day.